Hi, I'm Fan Mo from Imperial College London. I'm going to present our work, DarkneTZ, which is a deep learning framework towards model privacy at the edge by utilizing trusted execution environments. This is a joint work with Champaign, Kilominos, Sartorius, Elias, Andrea, and my supervisor Hamid. The story behind DarkneTZ is the springing up of deep learning applications on edge devices. One research has shown that in Google Play Store, apps with deep learning function has 5 million downloads in average, and apps without deep learning function only have 0.1 million downloads. Similarly, the number of reviews also shows that deep learning applications are 4 times popular than applications without deep learning function. Among those applications, 81% use deep learning as a core feature, and 71% are for image-related usage such as face recognition or image editing. On-device deep learning is popular, but the deployment of deep learning model leads to an issue of the model privacy. Deep learning models work because they memorize information, more specifically the training dataset. However, the training dataset could be sensitive or private, so the model can become one victim when one attacker is trying to disclose private information of training dataset from it. For example, the membership inference attack, MIA for short, has attracted so much attention from researchers. The attacker is trying to distinguish the presence or membership of one data sample in the training dataset. For example, by inputting your image into one disease recognition model, the attacker can know about your presence or whether you have this disease or not. To preserve model privacy, 2 common ways are obfuscation and encryption, such as differential privacy, noise addition, and homomorphic encryption. However, they usually cause a decreasing utility or increasing cost, which becomes impractical for edge devices with limited computational resources. Recently, one promising way to preserve model privacy is to run deep learning model with trusted execution environment, TE for short. The TE is designed to guarantee confidentiality and the integrity of the code and data inside. It is an isolated environment in addition to rich execution environment, RE for short. The isolation is established based on both hardware and software, and then it runs client applications and trusted applications separately. The TE can be very helpful. However, we did not see any work proposing deep learning framework at the edge. And most all previous research are aiming at cloud-like devices with Intel SGX. The edge device, such as mobile phone, which commonly has an ARM chip with trustzone, usually has much limited computational power. Besides, most of previous research designs frameworks for inference, but model training at the edge is also very vital, as there is a repeat development of edge computing and distributed or federated learning paradigm. In addition, edge devices have much limited computational resources provided by the TE. Therefore, we cannot simply put the whole deep learning model inside the TE. Actually, deep learning model is not like this. It is architecture with layers. So can we only put several layers in the TE? Then we can take another advantages of the layer architecture, that layers learn differently. According to many research, first layers tend to learn general information such as colors, and last layers learn specific information such as face identity. This means that layers may also memorize different information, and consequently have different privacy risks. One model prediction paper proposed to put several layers at the client side and the other layers at the server side for inference. But for training, the sensitive layers could be changed. The MIA on identity is one kind of high-level features, so the last layers probably are more sensitive. Therefore, we need to figure it out that how to partition a model and put several sensitive layers in the TE, and how to achieve a good trade-off between model privacy and the cost. Alright, now I'm going to show you our results and contributions first. We designed a framework named DarkneTZ to achieve a layer-wise protection for the model privacy. We achieved to defend against MAs with only 3% performance overhead without damaging model utility. When fully utilize the TE for potential attacks, we have a 10% performance overhead. Furthermore, DarkneTZ provides both inference and model training with an edge-like TE trust zone. The code is online. I encourage you to have a look and try to play with it. So let's go back and think about why and how we designed the DarkneTZ in details. In order to run several sensitive layers in the TE, we designed the DarkneTZ, which consists of two steps. The first step is model preparation. The model's several sensitive layers needs to be provisioned into the TE in a secure way. And the second step is model partitioned execution. Then both the forward and backward propagation of deep learning will happen across the REE and the TE. The server or the model owner only trusted the TE of the edge device or the model users. As shown in this figure, the trusted boundary. We consider a threat model that an adversary with 4 access to the REE of an edge device. This could be the actual user, malicious third-party software installed on the device, or a compromised operating system. Now let's look into the framework to see how it works. For the model preparation, it generally has 4 steps. First, the client application, the CA, in the REE requires the saved deep learning model in the hard disk or the SSD. And it also invokes the trusted application, the TA, in the TEE. Then, several non-sensitive layers are loaded into the CA, and the sensitive layers are loaded into the TA. We assume that the model is pre-trained using private data by the server, and it can be securely provisioned by the server to the client, and the sensitive layers are encrypted. After that, the TA uses the TE key to decrypt the sensitive layers, and now the model and all layers are ready for conducting inference or training. For the model partition execution, it generally has 5 steps. After all layers are loaded, we feed data into the model. Then the model does forward and backward propagation across the REE and the TE. More specifically, during forward propagation, the activation of the last layer in the REE is transformed to secure memory to the TE. And if one is using the framework for model training, during backward propagation, the error of the first layer with respect to the lost function in the TE are transformed back to the REE. After that, for inference, the framework normalizes the output in order to limit the information in the production or the confidential scores, and then output the prediction results to the REE. Or, for model training, the framework can encrypt the layers in the TE with TE key for secure storage, and then transform those layers and save the whole model in the SSD. One thing is worth noting that inference usually is for one data sample each time, but model training usually has many bunches of input data samples, so the forward and backward propagation will be persist for multiple times. We then conduct some experiment to evaluate the design framework. We develop an implementation based on the DarkneTZ deep learning library. We run the implementation on Open Portable TE, which provides both REE and TE designed to run on top of ARM Trust Zone. We use Haki 960 board, which is a widely used edge device, and control the CPU frequency to avoid underclocking. The Haki board provides 16 MB secure memory for the TE. We first test on 2 common models, Alex Knight and VGG7, on 2 datasets, CIFAR 100 and ImageNet Tiny. And we also have tested 6 more realistic models later. In terms of the symmetric, we used CPU execution time, memory usage, and power consumption to measure the system performance. We collect those information mainly based on process information in the REE and one Monzo power monitor. Besides, we used a state-of-the-art whitebox MA to attack the model and use the standard position and recall same to the reference as the metric of the model privacy. This is a simple demonstration showing how our implementation works. We run DarkneTZ on a Hi keyboard. In this terminal, I tap root command in order to have access to the X TEE. Then I run the DarkneTZ to train a classifier on mixed dataset, and the first 4 layers are in the REE and the others are in the TEE. Now it is running, and those several layers shows the system performance of one bunch of data. As you can see here, several first layers are in the REE, and the last layers, which has underlined the TA at the end, are in the TEE. Now, I'm going to show some of the evaluation results. Here, we incrementally add consecutive layers in the trust zone starting from the last layers. For model training, we found that protecting only the last layer has negligible effect on the CPU time, as shown in this figure, and fully utilizing the trust zone further increases CPU time, but the overtime is still under 10%. For inference, we found that protecting only the last layer increases CPU time by around 3%. However, it increases up to 10 times overhead when the maximum possible numbers of layers is included into the TEE. To investigate why the training and inference have such huge difference in terms of CPU time, we further analyzed it in user mode and kernel mode. As shown in the left figure, most CPU time for training are in the user mode, which is in the light green color. However, most CPU time for the inference are in the kernel mode, as shown in the right figure in dark green color. One reason is that since we only conduct one-time inference, the operations of invoking TEE libraries and creating the TA for the first time significantly increased the execution time. One way to take off this is to preload the TA before one-time inference. Regarding memory usage, training with the trust zone does not significantly influence the memory usage, as it is similar to training without trust zone. Inference with trust zone use less memory, but there is still no difference when more layers are placed into the trust zone. It is worth mentioning that those memory usage are in the REE. For the TEE, the TA uses a fixed mapping size of secure memory in total for all configurations. It is because that the TEE runtime allocates its memory for the TA, and it does not influence when more layers are moving into the memory. Regarding power consumption, it significantly decreases when more layers are moved inside trust zone during training. In contrast, the power consumption during inference significantly increases. In both settings, the trend of power consumption is probably related to the change of the CPU time. As shown in the figure, trajectories of them have the same turning points with the CPU time. One reason for the increased power consumption during inference is the significant increase in the number of CPU executions for invoking the request TEE libraries. However, when a large number of low-power operations such as memory mapping operations are involved, the energy consumed per unit time could be lower. We also test the performance of DarkneTZ on 6 models trained on ImageNet when protecting the last layer only. By doing so, we can hide confidential scores and the calculation of loss function for defending against MAs. The results show that the overhead of protecting large models is negligible, with no more than 2% for all models. In addition to that, we found amongst those models, the models with small sizes tend to have a higher rate of increase of CPU time compared to the larger models. This indicates that with larger models, the influence of trustzone protection on resources consumption could be relatively less. After system performance evaluation, we utilized white box MAA to test the privacy risk. Both protecting from the last layer and the first layer are evaluated. Our results show that when protecting the first layers in trustzone, the attack precision does not change significantly. In contrast, hiding the last layers can significantly decrease the attack precision, even when only the last layers is protected by trustzone. The precision decreases to random guessing. The results also show that the membership inference information that leaks during inference and fine-tuning is similar. We further evaluated the privacy risk with only protecting the model's outputs in trustzone by normalizing before outputting production results. We conducting the white box MAA when all other layers are accessible by the adversary. Three combinations of models and dataset include AlexNet, VGG7, and ResNet on CFAR 100 are selected as they were identified as more vulnerable to MAAs. DarkneTZ is set to control the model's outputs in three different ways. The results show that all three methods can decrease the attack success performance to random guessing. Therefore, we conclude that it is highly practical to use DarkneTZ to tackle MAAs. To summarize, we proposed to protect the last layer using DarkneTZ to defend against membership inference attack on deep learning model at the edge. We also found that protecting the last layer in an edge-like TE results in no more than 1% overhead for training, and no more than 3% overhead for inference. For protecting layers the TE can hold to defend against other potential model privacy linkage, it results in no more than 10% overhead for training. However, one-time inference still requires further investigation. One way to tackle it is to utilize preliminary load of the TA, which could be an interesting attempt in the future. In this research, we have answered two questions. First, is it practical to store and execute a sequence of sensitive layers inside the TE of an edge device? We showed that the answer is yes. And second, are such partitions useful to both effectively and efficiently tackle realistic attack against deep learning models on edge device? We showed the answer is yes, and how can we achieve it using DarkneTZ framework? However, there are still many unanswered questions. For example, can we use model compression to include more layers to make maximum use of the trustzone? Second, can we use specialized processors to accelerate deep learning with the TEE? In addition, we expect there are more cases that people can adapt DarkneTZ framework to do on-device training. Thank you for listening. Please check our paper and codes for more details. And now I'm open for your questions.